Welcome to lecture 6 of MCS 507, a course on mathematical, statistical, and scientific software. So as you can see, the topic of today is root finding methods, but it is in our third week where we explore Python. We will see files and the operating system module or the operating system package. The topic of this week in general is interfacing with other mathematical software. So in the central part of this lecture, I have the mentioning of OpenXM and OpenMath. So these are protocols for exchanging mathematical information. The application or the context for this lecture are root finding methods. And root finding methods are used to define algebraic numbers. So in a way, the mathematical theme of this week is also arithmetic. I will say something about double-double arithmetic, interval arithmetic, and algorithmic differentiation in this week, while we are more exploring Python. Okay, so let me start with NumPy, SymPy, SageMath. So root finding is a fundamental problem, both numerically and symbolically. I will try to indicate how you can view both approaches. So symbolic computation is concerned with rewriting. And on this slide, I will derive the companion matrix of a polynomial via a rewriting rule. If you say that x to the power 3 plus 2x minus 1 equals 0, then what you actually are saying that x to the power 3 equals minus 2x plus 1, provided x is of course a root. But let's say that x is just any symbol, and we can compute with that symbol if it is a root. What does that mean? It means that if x to the power 3 can be written as minus 2x plus 1, that actually we can write all higher powers of x higher than 3 as a linear combination of x squared, x, and 1. So the derivation of the companion matrix is often presented as a transition to an eigenvalue problem. And indeed, so the bottom expression here says that x times a vector with the powers of the roots equals a matrix times the vector of the powers of the root. So replace x by lambda, and then lambda, the symbol we usually use for eigenvalues. Then you see that the companion matrix, the eigenvalues of the companion matrix, and here you can see that we can be flexible. The first row consists of the coefficients. So this is how the first row expresses x to the power 3 as minus 2x and 1. And then the other rows express that x to the power 2 can be written as indeed x times x. I read this now from right to left. And then x is x times 1. Okay, numerically, so let's see how we can compute all roots numerically as an eigenvalue problem. So there is also a roots wrapper, and now I mentioned PyLab, so that's still an ancient, well, not ancient, so that's a precursor to the Jupyter notebook, and one can still run Python in that way as PyLab. I've de-emphasized this a little bit now in this run of the course because we have Jupyter. But the main point is that if you have a good method to compute eigenvalues, then also you have a very good numerical root finder. In the other way around, eigenvalue methods also rely on techniques of refining roots. Okay, what is now the symbolic way of doing this? Okay, so one has the quadratic formula, but one also has the cubic formula. And here you see you learned the quadratic formula very early on. And you can see already from the cumbersome and the polynomial x to the power 3 plus 2x minus 1 is actually a simple cubic. But you see why the cubic formula is actually generally not thought not seen in mathematical elementary classes, but it exists. What I'm using with this command here, with this illustration here, is not to disparage at any means symbolic computation, but just that the output roots in one context may mean something entirely different in another context. So in symbolic computation, the default is working with symbols. And if you look at this, it's not that bad. We essentially have a dictionary where the keys are the values, and you see 3 times 1, you see that there are 3 simple roots. So the root finder from SymPy will actually be a lot better when it concerns multiplicities. And it is exact. So computing multiplicities, dealing with multiple roots numerically, is not far from being trivial. Symbolic computation is actually very good at handling singular situations. Okay, but then roots itself, so here I'm doing everything still in an interactive session. The same SymPy and the same roots, when you give it a dotted numbers, will actually give you a numerical result. And now also with the multiplicities. So you see that every cubic with real coefficients has 1 real root and 2 complex conjugated roots. So then there is also the solving with symbolically, so with parameters. So one can ask the roots of an equation of a polynomial here in 2 variables. So we can compute the roots x squared minus y, compute a symbolic square root. And we can also do this with a parameter. So in a way, in a lot of very important problems can sometimes be reduced to a quadratic or a cubic relation with a parameter in there. So in a way, the root finder here geometrically eliminates the parameter or separates the leading variable, the most important variable, from the parameter. All right, Sage Math. adds another layer of sophistication. So we can specify the coefficients. So we already have seen with SymPy, if you give 2 or 2.0, you get other output. Now we have the integers and the reals. Here we declare x to be a variable for polynomials with integer coefficients. If you then ask the roots, so here I constructed a root with one integer, with one integer root, then it's a degree 4 polynomial. And I asked for the roots, and I get one back. I constructed my polynomial deliberately that it had a root, because for most of the case times, if you write down a polynomial with integer coefficients having real roots, having integer roots, is quite unlikely that you're going to find an integer root. But if you're interested only in the real roots, you can specify in the argument of roots, like it's done here with the ring, RR is the real ring. Then you see that this quartic polynomial has two real roots. So in addition to the integer root 1, there is a real root 0.45 something. And if I want to know that root with 100 bits, compute that root with 100 bits of precision, then I can also specify the 100 in there. So you can see this is kind of twice the 52 bits of precision that we would have with the normal floating point precision. So it depends on the coefficient field, what output you get. So there is the field of the coefficients, but then there's also the type of coefficients of the roots. So here we have twice the same polynomial with integer coefficients, but once we ask the roots also over the integer coefficients, and then twice we ask over the 64-bit floats, the standard ring here, and once we ask with 100-bit floats. So Sage provides a very good syntax for this. We can also compute all the complex roots, and here you see that we are following very much the syntax of SymPy. We can leave off the multiplicities if we know that our polynomials, or if we don't care about the multiplicities. And then we can combine, so there is real field, there's also complex field, and where we can provide the number of bits. Okay, so this is just a flavor of how root finding can be done, either with standard numerical libraries from linear algebra, or wrapped into Sage, which, depending on the field, will resort to a numerical root finder. When you want complex roots, so complex roots now by default are numerically, or whether you want over the rational fields would be QQ, by the way. Okay, so I'm going to transition to MPSolve. It's a standalone solver. But in the meantime, I'm going to say something about wrapping programs. So we're going to do three. I'm going to mention OpenXM and OpenMath. The OpenXM philosophy, as I understand it, can be quite simple. You provide a binary, an executable program. So that's the approach that we are going to follow today. This is extremely flexible. It suffices that somebody gives you an executable version of a program, and then you can wrap it. You can wrap it so the program, you may even not know or don't care in which programming language that it is written. You only care that you can formulate the input and process the output. And Python is actually quite suitable for that. We will see that wrapping executable versions is similar to file processing. And in a way, that's very useful to do. OpenMath is a more elaborate standard. So there's a unfortunate typo, it's mathematical programs. I will fix that. So OpenMath tries to define how mathematical objects are represented. So you can think of a polynomial, that's a universal mathematical object, that you would have a standard of how that object can be presented, and once all the programs follow that standard, or if interfaces are written with respect to that standard, you can capture as much as the meaning of that object. And that's far from trivial. Polynomials numerically are represented as their coefficient vector, but with that actually you already lose a lot of information. You then lose the information of, for example, whether the polynomial factors or not. Sometimes polynomials are better represented in factored form. That's what you lose. You also lose the coefficient type. Now in numerics, the default type is 64-bit float, so you may not want to worry about this. Now the story then becomes a lot more complicated when you talk about solutions. What type of solutions do you want? Again, one can indeed say a solution to a polynomial is an algebraic number. So that is the mathematical view of seeing things. And we've seen actually that with the numerical output, you can reconstruct your algebraic numbers. So we've seen this in the first lecture with the PSLQ algorithm. But also this reconstruction is already a computation. So how much in your object representations do you encode as an algorithm, or can you recompute things? Okay, for this lecture we are very practical minded and we wrap executable versions. Interfacing software is a very important task, and that could be, if you're interested in further research topics, that could be a way how programs talk to each other and how to standardize this as much as possible. That's an important topic. A problem that actually Sage has solved to a great extent. Okay, what are we considering for the remaining part of this lecture? MPSolve is a multi-precision root finder. So it's a numerical program, but it goes to arbitrary precision. The original version was written in the last century, so in a way it's a mature program, but it has evolved. So last time when I developed this course in fall of 2019, I was happy to see that the current version is actually licensed under GPL and has a GitHub. So I updated the current version 3.2.1. So the algorithm is quite involved. So it is based on simultaneous iteration, and at the same time quite robust. So it can handle very pathological polynomials. So in a way, there is this program, and then there is also another program whose name escapes me now. But there are two. There are actually other programs out there. I'm sorry. Sage actually also. Also, I'm sorry for blanking out a little bit. Sage also has various state-of-the-art solvers. But let's assume that we want to use MPSolve, and MPSolve has a very straightforward interface. Here it is. So for our quadratic, from the beginning, we write the input file. So the coefficients are given as a sequence. So the degree comes first. So I'm sorry. So this is the example. The coefficients are -1, 2, 0, and 1, and it's a cubic polynomial. So you should read the coefficients backwards. So the point here is that MPSolve runs at the command prompt, which in a way seems to be old-fashioned, but is in some sense very flexible for input-output. So it takes on input, a command line, and then by default it writes it to screen, but you can redirect the output with a larger than symbol to output. Okay, it works. Here you see the output, which is written in the standard notation, the floating point scientific notation. So we see indeed two complex conjugated roots and one real root with a zero imaginary part. So representing complex numbers as tuples is in some sense very standard and very convenient as well. So one doesn't need to worry about what is now the standard convention for the imaginary unit. Is it the little j, is it the little I, or is it the big I from SymPy? So simply work with tuples. So it is a numerical program, but made robust with multiprecision. Okay. So we will extend Python with the solver. The standard way to interface data is via strings. The standard way is probably a bad way of saying this. When we considered object-oriented programming, I was saying that it's very good practice to define the string representation immediately after the definition of an object. So in Python, every object has a string representation, and you can turn any string into the object by evaluating this. So exchanging information between programs is essentially interchanging strings, sequences of characters. And that's the most basic and actually also the plain computer science way of interfacing. So we just have sequences of bytes where one program talks to the other. Here we will using files. When it gets to client-server interactions, they will be replaced by sockets. So whether you have two programs talking to each other, it's the same principle when you have setting up a web server or when you are working on a graphical user interface where the user interface is separate from the program that does the computation. So what we will do is we will make our first module. The module is called call MPSolve, and it will mainly export MPSolve. So in a way, the cool we mentioned modules before in the second lecture, but I really didn't say how to make a module. It's also defining your own modules is a way of extending Python. So in that sense, Python is extremely extendable. All right, how do we do this? Well, so ultimately we will run MPSolve. So that's at the center point of our interface. So we will make an input file. So what the user types in as input to the string will be written in a file in a format that is understandable to MPSolve. So that's one step. So extracting the information from the string to the input format of MPSolve. Then the second part is the extraction of so we have the redirection of the output to a file. Then we will extract that information from the output file into a format that is convenient to process. So the list of tuples again. All right, how do we work with files? So this was prepared on a Linux workstation where if you have Scratch files, you have the /tmp, the temporary drive. On Windows, you have to replace this with something. You don't have a /tmp, but the syntax remains the same. You open a file with the name, first string, and you open a file for writing. Then you can close that file object, and here you can see that we can now read that file with another name. So I open the file now, but I open the file for reading. And reading everything from file is very flexible. We read lines. So that's another advantage of working with strings. The string format is a readable format. So one could say that's again losing a lot of information, but for our purposes here, it actually works. But you can see how one can object to this. So one has the information of a polynomial in one session, and one actually wipes all that information out. So the type of coefficient, for example, the structure of the polynomial, it's actually all written into a string, and then another program is going to interpret that string. So within that interpretation, there is a lot of information that get lost in the interface here. So that's why it is a working option, but it is somewhere the first attempt that you should make when you make an interface. So I would also say that if you cannot interface in this way, it's going to be very hard to have the programs communicate with each other. So that's also something. This type of interface also works quite well if the amount of computation is quite considerable. So in this week about arithmetic, you do actually not want to write a file for every arithmetical operation that you're executing. So root finding can sometimes be computationally intensive, especially if you want to go to higher precision and if you want to solve pathological cases. But for arithmetic, this is actually not really the good way of working. We will see more efficient ways later this week. Okay, Python is said to be also popular among system administrators because you can do to write kind of general system administration regardless of the specifics of an operating system. So if you are building your interface, you may want to have it run on a Windows computer or on another computer, on a Linux computer, and the removing of a file name is different on one operating system with another. So there is the remove on remove of a file that will work whether you work on a Windows computer or whether you work on Linux computer. But here, most importantly, and I should have indicated that first. So here the removing of files is useful because you may want to wipe out the temporary files, so the input files. So what we will do with our interface, we will make an input file, and the input file only is meaningful for that one particular polynomial that we want to solve. So we may want to remove this later on. Otherwise, for every call that we do, perhaps in the debugging stage, you do not want to remove it. But if you go to production stage, you actually want to remove all the input files. Okay, with system, you can run any system command. So here I executed this on a Linux station. I think it was on a Mac, it was not on Linux, it was on Mac. And I could check whether a file was there or not. So if it is there, then it will return 0. 0 means no failure. After I have removed it, then you see that there is an error message. So the error message comes from the output of the ls command. But then there's also the 256, which is returned to the Python program that made the call. So it's also possible to actually check on that. And then again, there are exception handlers, which we will cover at a later point in this course. Okay, now here comes the code for the module now. So extracting the coefficients from a string representation can be very, very involved. Parsing a polynomial. But with SymPy, it is not that bad, especially if we here restrict our input to polynomials in X. So having a more flexible interface would essentially allow that the user fixes, also provides the symbol rather than having it fixed to X. So, what happens here in the first two instructions in this function here, so this function will prepare the string that will be written to file. So it will define, in the context of SymPy, it will define the variable x and evaluate the string, the given string, into a polynomial. So then I have an expression, a general SymPy expression, which I turn into a polynomial object. So the qpol is a polynomial object, and with that polynomial object, I can ask for all coefficients. So that's a method that's defined on an object belonging to the class poly. So the coefficients for MPSolve have to be represented with the lowest degree term first, so first the constant. So I reverse all the coefficients. So the first 5 statements are actually very short, and they deal with all the parsing here. There are exceptions here that can happen. So if the user, and this is where exception handler needed for a more user-friendlier interface, which are not done here. So there are only these 5 instructions. Okay, then in the second part, we prepare the string using the particular MPSolve interface. So we have the coefficients So we have the first statement is actually a documentation string. So I should probably have pointed this out in the beginning, but the exclamation point means that MPSolve will ignore it. So this is the string representation of the input polynomial. Then a new line, and then the field that we are working with. Double, real, imaginary. So we will also get the complex roots. Okay, then we have the degree information after a 0, and now I'm blanking a little bit what the 0 really meant, but it worked in the case here. And then we write the string representations of the coefficients. So this will result in one long string, and the virtue again of working with strings is that as we develop the module, we can look at it. So we can test this also independently. And copy and paste to a file and then run MPSolve. So that is actually the first part of the interface. Okay, now our temporary files, we could always write to input file, but that will give a problem the second time when we run the interface, and if we don't clean up. So we will have random names. So I will make a random number of 8 digits long. So here I'm calling the random number generator. I take a string representation and I add this to my input name. A little bit more sophisticated, you could actually add the date to it, for archival purposes. Okay, so we have the preparing of the input and the writing of the input file, with the making of a random file name intermediately. Okay, most of the work is actually done already. We want to provide the interface may want to be a little bit more extensive. So when we run the Python program, we may want to provide already where is the location of the MPSolve executable. Here we use the sys module, and if you have ever programmed in C or C++, it is using the same argv, the arguments, the list of strings at the arguments at the command line. So the first we actually check whether the arguments are 0 or not. So and we can actually check whether there are arguments or not. The raw input here may be an old Python 2 construction. I'm sorry for not updating this. But this gives the prompt. We also make actually our program interactive. So it will get the absolute path name where the executable is. That was either provided at the argument for the Python, or it will prompt for it. Okay, so that was the first part, launching. Then we continue the methods. So here are the other methods. We are extracting the information now, reading all the lines from file, and then evaluating all those lines. Remember, from the output we had a sequence of tuples with the real and the imaginary parts. Here it's actually quite good. So we're going the eval, we have the string representation on every line. There is a string representation of a tuple. So for all the lines that we have read, we're going to have a list of tuples. with Python doubles. Okay, so then the main program that we export. So in a way, I should have mentioned this also as well. This is a pure functional modular approach with the main program. So here is the main program. Although I was thinking bottom up, I was actually also thinking top down. So this is the main program that gets exported. So there is a default location for the program um, that is taken if it is valid. So we will take the polynomial, prepare the input, write it to file, and then also the output file will also have this randomization in the name. So we run the program, running the system command, and then we extracting the roots. We're removing the input and the output file, returning the list of tuples. Okay, so in a way, this works. It's also a very truncated usage of MPSolve. So I'm actually here using the standard doubles. A better interface would actually use the MPMath to to evaluate the programs, would actually also to evaluate the output. So in case we use multiprecision arithmetic. Okay, that's the end of it. So I have deliberately not overloaded my slides. There are two types of two types of exercises. So the first type of exercise is concerning root finding. So you can look at the roots x minus 1 to the power 20. So, and that's an example where there's only one root. But if you give this to a numerical solver or to and here actually I did not specify which solver, so I now see that this exercise is very badly formulated. It's not going to be an interesting exercise if you are using SymPy or a symbolic root finder, because that will give you entirely one. It's going to be interesting if you ask this to a numerical root finder. Okay, so you can simulate this. In Sage, you can add a small change to it. Then Sage is actually forced to take this changed polynomial. So we have a multiple root, a polynomial with a 20-fold root, multiplicity 20. And the problem that this is hard is that polynomials that are very nearby also have roots that are very, very nearby. So this problem is very sensitive to changes in the input. So if you have taken numerical analysis, then this type of looking at it is very familiar to you, or should be familiar, or could be familiar. If not, it's mainly intended to see whether the programs actually produce the output what you would expect mathematically and numerically as well. So x minus 1 to the power 20 is difficult if you work with a system with limited precision. So the machine precision is the smallest number that you can add to 1 and still make a difference. So this is in the third exercise used here. So at some point, if you use a numerical solver, adding an epsilon that is less than the machine precision does not make sense anymore. Okay, so here is an interface exercise, and perhaps to motivate you, so I took this from the take-home version of a former midterm exam. So it could be good if you're interested in root finding that you would do an exercise with MPSolve. But here is a more general exercise. Suppose that you have two Python interpreters. They could have several versions, and one version has NumPy, the other one has not. How could you extend the other one so that you can use the facility with NumPy? So, in some sense, this is simulating that you have software that is either legacy or is either too specific, or that you want to use multiple versions of Python systems where one Python system is extended with a numerical type of interface, the other one with a different. So design an interface so that one interpreter takes in a matrix and calls then the other interpreter, so via the system command. It could be the same. So you could pretend, so you can run twice the same interpreter. So you don't need to install, if you want to solve this exercise, you don't need to have two different versions or two different versions of Python installed, or two same versions at different executables. You can run the same executable. But pretend that interpreter A then doesn't have access to NumPy. And as a check, you could then have interpreter A, if you use the same interpreter, you can do the check. Okay, so this was it for today. So we have seen how to work with files in Python, how to call system commands, which is useful to call other programs, and that in turn is then used to build interfaces where one needs mainly or only the executable version of a program, and that's it, to use the program from within another program.